I'm the Chief Scientist of Tactical Computing Labs. I just wanted to give a quick overview of who we are. We've had several people come up to our booth outside and say, okay, the logo's cool, but who are you and what do you do and why are you at a space conference? So in terms of the history of TCL, so we were actually a completely self-funded startup. We started in 2016 in the high-performance computing space. We're actually effectively a private national laboratory. So we are completely private, but we operate much like a national lab in the US. So we do a lot of work in HPC. That's a lot of our background in our previous research life was in the high performance computing and scientific computing space. We do a lot of work in AI and ML since we actually have an internal compiler team. Every new AI startup in the world needs a compiler, so we do a lot of compiler work there. We also do a lot of work in the US government space as well as the space industry. So academically, I'm also an adjunct professor at Texas Tech University, where I do quite a bit of outreach and student advisement and whatnot. Professionally, I am also the technology horizontal chair at the RISC-V International Committee. So those of you who during your talks are discussing, the potential to create a RISC-V for space SIG, you actually have to talk to me first. So if you're interested, come by at lunch and we can actually figure out how to do that, because under my purview is actually all of the various different market horizontals in which space is, of course, there's nothing there at the moment. So we also have David D'Onofrio. He's our chief hardware architect and the other company principal. He has a tremendous amount of experience in high performance computing. He formerly ran the computer architecture group at Berkeley National Lab. So what is TCL and what do we do? So we're actually split sort of three ways internally. So we have a hardware development group that, needless to say, focuses a lot on RISC-V development, but we also do custom microarchitectures. We do custom prototyping in terms of FPGAs and ASICs, and we've done this for quite a few different people. We've actually worked with the Army Research Lab. We have two very large RISC-V projects with IARPA at the moment. We're actually building what we call in the US leadership class data-intensive supercomputers entirely based upon RISC-V. So these are multi-million CPU systems based entirely on RISC-V technologies. We did an initial evaluation of RISC-V for NASA, actually as a small business innovative research program. And we, of course, participate in the RISC-V groups. So those of you who are familiar with RISC-V software ecosystems, we do a lot of work with the linear algebra infrastructure, specifically Bliss and Flame. We do a lot of benchmarking and prototyping. Many of the benchmarks that we work in are sort of sparse or sparse linear solvers. And then we have a compiler and system software group that works with programming models, runtime libraries, and various different compilers, both GCC and LLVM. But we do a lot of work with the Department of Energy's template metaprogramming infrastructures. So I wanted to talk a little bit today about co-design for RISC-V infrastructure. So the whole onus of why we're all here is RISC-V is this wonderful open hardware ecosystem where we can experiment with new instructions and new extensions and variations in the microarchitecture to implement what's effectively application-specific or market-specific microarchitectures and implementations to accelerate our particular scientific or sort of market vertical applications. So I wanted to start with a bit of a jest. So this is what I call the stages of isomodification. So when I go back and do seminars at the university level, one of the questions I ask my students is, if you could have any instruction, what would it be? And much like the audience here, you sort of have this like heartbroken thought of, well, if I can have any possible instruction, what would it be? And you get some really bizarre answers to this. So I took this slide, or I sort of modified this slide from a colleague of mine, Kathy Yellick, who used to be the Associate Director of Computing Sciences at Lawrence Berkeley National Lab. Her original slide was the stages of artificial intelligence adoption in scientific computing. So this is the stages of isomodification. So we start out with denial. I can just infinitely accelerate my software. The algorithms will be better and it will all just work. It'll be wonderful, right? And then we sort of stop and realize that, oh, well, maybe not. Maybe we actually do, and maybe we do have the possibility of adding additional instructions or collapsing instructions to do something interesting. And then there's this sort of phase of depression. And that phase of depression is, oh, I can't do this as a single person. I actually need an RTL team. I need a DV team. I need a compiler and system software team. And now there's people who need to understand operating system drivers, and your head sort of starts to spin. And then there's this sort of phase of optimism of these people actually exist. The RISC-V ecosystem provides a wealth of experience with a wealth of expertise to actually go do this. And then the next stage is this. So you get to this point where there was this really interesting idea up front, and by the time you get to the end, there is so much confusion and so much sort of muddied effort that you sort of forget where you started. So at TCL, we've sort of gone through this process now about a dozen times with various different RISC-V designs for everything from high performance computing to embedded defense operations to the space industry. So this is sort of what this started out as for us. So we start with performance modeling. So we write benchmarks, we pick benchmarks off the shelf, we start looking at the assembly code, we start doing hand optimizations of assembly, which is incredibly expensive from the human perspective. And then we move into specification. Okay, now that we understand what the applications are doing, how do we echo that back into some sort of ISA specification or ISA extension? In this case, we actually developed an ISA extension for RISC-V that allowed you to do distributed node shared memory access across the supercomputer without changing the application binary interface, which was huge. And this took years of effort to actually put this together into just the specification. So then we take that specification and we start doing modeling and simulation. We all love models, we all love simulators. And what that really means is we all hate models and we all hate the simulators because they're always too slow and they're always inaccurate and they never give us the performance results that we need. So what did we do at TCL? Of course, since we're researchers, we wrote our own simulator. So we actually have an open source RISC-V simulator called REV that runs inside of a parallel discrete event simulation framework called SST. It actually allows you to do full system RISC-V simulation using a completely open source model where you can plug in modular sets of networks, memories, CPUs of different sorts, homogeneous, heterogeneous, the whole suite. And then we do the implementation. And this is where Dave comes in and says, Dave, John, actually your Verilog looks absolutely horrendous. Please go sit down in the corner. And our RTL team spins up. We start doing chisel development. This is actually real RTL out of a machine that we're developing that has dual CXL HBM capability, which is a very interesting implementation for high performance computing. And then we do performance tuning. But as you see, this whole undulation of effort is actually sort of this linear curve of effort. So by the time you get to the end, you've expended potentially years of effort to get to the point where you may or may not have a performant product. So this is actually what we've done over time is we've taken this sort of linear effort of development with developing all these point technologies in software simulation, verification, and performance analysis and integrated it into this sort of cyclic set of co-design efforts. So what we actually start with is we actually start with specifications. So rather than start with performance analysis or ideas, we actually start with the specification as the central point of this co-design effort. And more often than not, we start with RISC-V. We've done other things, but we really like RISC-V from the simple point of modularity. And then we start, depending upon what the project is, we can actually start at any point in the curve. So on the top left-hand side, as I mentioned, we have this open source simulator called REV, and REV allows us to do full system modeling. Well, the nice thing about that is we can actually use our current generation of supercomputers to simulate the next generation. And this is quite a literal fact, because using REV and SST, we've actually been able to simulate a 70,000 CPU supercomputer on our current supercomputer. And that is cycle-based CPUs, memories, caches, networks, soup to nuts, running actual applications compiled with LLVM and GCC. So that's a very, very different paradigm than taking a basic trace and sort of putting it through a simulator that runs on your laptop. Of course, not everyone has a supercomputer. Thankfully, we have a small one, and we have a lot of friends in the US who have very large ones. So, you know, it's sort of one of those like friendly agreements of getting access to computing time. And then we have things with RTL implementations. So those of you who do RTL are very familiar with Verilator. Unfortunately, Verilator can be very slow, and it doesn't always interoperate with other things. So what we did is we actually developed some open source infrastructure that allows us to take Verilated modules and plug them directly back into the simulator that we wrote using SST. So you can actually do co-simulation now and co-emulation of Verilated models of any portions of memories, networks, and CPUs directly next to the functional models you also developed. So you can actually run both of them adjacent to one another in the actual same simulation. Or you can build them such that you do full functional simulation and then do verification with the same framework using your Verilated modules. So, as I said, all these things run actual real binaries, and with these binaries, this allows us to run full C++ applications, including parallel applications. We do a lot of work with Raja and Cocos, which are the DOE exascale programming models in the US. And then we do all of our numerical algebra and tuning on these simulation models and those co-simulated and co-RTL models. And this all wraps back around to the point where we can do very, very rapid design and very rapid evaluation of these infrastructures. So, for example, Alexandra this morning was presenting the EPI effort here in Europe. We have similar efforts going on in the US, one of which is the IARPA Agile effort, and we're doing the exact same process, and the US government gave us 3 years to go from pure design to synthesizable RTL and full runtime stack and full programming model stack in exactly 3 years, which is absolutely insane, but it's a tremendous amount of fun to actually do from an engineering effort. But specifically for space, this is actually an effort that we took the same approach on, and we used to build a modular radiation hardened infrastructure that we called RAD-RISC. So RAD-RISC is effectively a RISC-V rocket core that we modified with different variations of triple modular redundancy and software-based checkpoint restart infrastructure that was built directly into the compiler. This was all actually built using the same flow, using the same simulation infrastructure that's still open source, that actually allows you to do simulated variations of various different gamma and alpha ray attacks on your simulated cores, using different random seeds, and that you can actually target different portions of different pieces of your simulated CPU. So you can actually look at just the memory side attacks and doing single and multi-bit corrections and detections. You can look at just the ALU and pipeline attacks, and all this is actually performed directly in software. And what we actually delivered to NASA was sort of this basic modular framework to sort of tune, based upon what your spaceflight vehicle and target was, how much radiation hardening and how much protection you actually had to put into the circuit and into the software ecosystem. So this is just one example of space-specific things that we're currently working on here at TCL.